Have you ever stared at a smartphone spec sheet and just felt totally lost in that whole alphabet soup of tech jargon? Well, you are definitely not alone. Welcome, everyone. In today's explainer, we are going to decode those numbers and acronyms together so you know exactly what you're buying. Okay, let's dive into this.
So, here's our roadmap. We're going to systematically decode everything here. We'll start with the smartphone's brain, break down cores and threads, look at clock speed, explore the power of nanometers, and finally, piece together the complete system.
All right, section 1, the smartphone's brain. We're going from macro to micro. You can think of a processor literally just like a human brain. You know, our brains have interconnected blocks handling entirely different activities, like one area for memory, another for motor control. Well, a processor is built exactly the same way. It's a tiny physical chip packed with dedicated blocks for things like memory, gaming, or multitasking. But here's the catch. Not all brains are built for the same lifestyle. PC processors, like those from Intel or AMD, they're built almost entirely for raw, high performance. But smartphone processors, they have a much harder job. They have to perfectly balance that performance with high energy efficiency. Because, let's be honest, it doesn't matter how fast your phone is if the battery dies in 10 minutes, right? So, to solve that battery problem, modern smartphone processors basically divide and conquer. They use power-hungry, big CPU cores to handle the really heavy tasks, like gaming or high-speed video editing. But for your normal, everyday chores, like making a call or sending a text, they seamlessly switch over to little CPU cores that just sip power. By separating the heavy lifting from the basic stuff, your phone manages to give you amazing performance and great battery backup all at once. Moving on to section 2, cores, threads, and generations, inside CPU architecture. This is where we figure out what those constant series and generation upgrades actually mean. Okay, so whenever a new generation drops, you inevitably hear the word cores. But what exactly is a core? I want you to think of a processor as a house, and the cores are the rooms inside that house. Dual core means you have 2 rooms. Quad core gives you 4, octa-core gives you 8, and hexa-core gives you 16. It's pretty simple. The more rooms you have, the more tasks can happen simultaneously. Just like you can have someone cooking in the kitchen while someone else is watching TV in the living room, having multiple cores means you can have multiple ops open and running at the exact same time, and your device won't even break a sweat. But what if you need even more multitasking? That is exactly where threading comes in. Threading is the virtual, actually let me emphasize that, it's the virtual, not physical division of a core. Imagine you're chatting on WhatsApp and listening to background music. A single physical core can virtually divide itself, spending, say, 75% of its power on your chat and 25% on your music. Because of this clever virtual division, a dual-core processor with threading can actually act like a super powerful quad-core processor. That's why you absolutely want to look for threading capabilities when you're buying a device. All right, section 3, clock speed and transistors, measuring the speed. We've talked about how tasks are divided up, but how do we actually measure the raw speed? Well, it starts with the term you'll always see on the box, clock frequency, which is usually measured in gigahertz. Now, giga basically means 10 to the power of 9, or 1 billion. So let's break down the math real quick. If you buy a processor with a clock frequency of 3 gigahertz, you multiply 3 by 1 billion. That means your processor is executing an incredible 3 billion instructions in a single second. 3 billion. How is that physically possible? Well, check out this number. 15 billion. That is how many microscopic transistors are packed inside an iPhone 13 CPU. A transistor is essentially a microscopic electronic power switch. Just like the literal light switch on your wall, it can only do 2 things. Turn on, which the computer reads as a 1, or turn off, which the computer reads as a 0. These billions of switches are turning on and off at blinding speeds to process those billions of instructions. So what does this all mean? Does a higher clock frequency always mean more speed? If you see a massive gigahertz number on the spec sheet, is it automatically the fastest device? The answer might actually surprise you, because no, not necessarily. The underlying architecture of those transistors matters just as much as the gigahertz. Think about it like this. Imagine 2 people are tasked with lifting 100 bricks. One is a 60-year-old and the other is a 20-year-old. Even if they are given the exact same task, the 60-year-old might take an hour, while the 20-year-old finishes in 50 minutes. Why? Because the 20-year-old just has more native energy and power. Processors work the exact same way. Even at the same clock speed,
A newer processor architecture is going to finish a task much faster than an older one because it operates with fundamentally better energy efficiency.
Which brings us to Section 4, the power of nanometers, shrinking the distance. If you want to know if a processor has that 20-year-old energy efficiency we just talked about, you need to look for NM, or nanometers, like the 5nm Apple A14 Bionic, for example. A nanometer represents the physical distance between those billions of transistors, and it is so microscopic it's entirely invisible to the human eye. Here is the golden rule you need to remember. The smaller this physical distance is between the transistors, the faster the processor's speed becomes, all while consuming far less battery power. The electrons literally just don't have to travel as far. Okay, last one, Section 5, Beyond CPU, the complete system on a chip journey. Now, we've talked a lot about the CPU, but the CPU is actually just one single block on the processor. The chip itself is a massive, interconnected system. You've got the GPU managing images and videos, the modem handling your internet data, and the DSP taking in audio from your mic. But honestly, the real unsung hero here is cache. Cache is a tiny amount of high-speed memory. We're talking maybe just 2 to 12 megabytes, sitting right next to the processor. Think of it like driving a car. You don't need to relearn how to hit the brakes every time you stop, right? The cache stores those highly frequent, repetitive instructions for instant access, saving the processor from having to look them up on the hard drive every single time.
So how do all these separate blocks actually talk to each other? Well, through the network on chip, or NOC. These are literal 128 or 256-bit data highways made of wires connecting every single block on the chip. And much like a real highway system, these wires use internal routers and switches that act exactly like traffic lights. They make absolutely sure that data traveling from the CPU to the GPU gets directed to the right place, on the right path, without causing a massive traffic jam.
To really see how beautifully all these components work together, let's track the journey of a single photograph, which happens in literally a fraction of a second. When you click your smartphone camera, it captures a massive amount of raw data. First, that heavy, unfiltered data travels over our data highways to the RAM. From there, it gets sent to the ISP, the image sensing processor. The ISP acts kind of like a photo editor. It fixes dark areas, removes unnecessary visual info, and maps every single red, green, and blue pixel. Once it's all filtered, it goes to the GPU, which perfectly resizes the image to fit your screen. And finally, it hits the display engine and boom, the picture pops up on your phone.
I mean, really think about what just happened there. As this quote highlights, an image containing millions of pixels travels through all those different blocks, getting mapped and resized in a fraction of a second. The sheer scale of it, the coordination of billions of transistors, and the blinding speed happening inside your device right now, it's just mind-blowing. It's essentially a modern miracle. So, I want to leave you with this question. Next time you read a spec sheet, are you going to look past the marketing numbers and see the billions of microscopic decisions happening right there in your pocket? I really hope today's explainer gave you a whole new appreciation for the device you're probably using to watch this right now. Thank you so much for joining me today, and remember, always keep seeking out high-quality knowledge to expand your understanding in the world. Catch you next time.